Hi, everyone. Next up, I am excited to introduce Josh Wells, a friend of mine and a longtime MLconf presenter. Josh has presented for us from multiple companies over his career, and now he's an unaffiliated developer in data science who was recently tapped by DJ Patil to do some interesting research around COVID data. And I'm excited that he's going to share this with us today at MLconf. Please help me welcome Josh.
All right, let's see if this works. Hello, can people hear me? Is this working? I don't really know much about computers, so I want to be sure I'm doing this right. I'm not kidding, I don't actually know anything about computers, sorry. All right, Courtney says yes, so I think we're good to go. All right, thanks everybody. So yeah, let's see, let's get going here. My name is Josh Wills. I refer to myself as a developer without affiliation because I don't have a job right now and have not had an official job for the last year. I used to work at Slack. I worked on data engineering and search. Sorry, what?
Oh, sorry.
Oh, okay. Well, that's all right, Ben. Ian's having a good conversation too. So I used to work at Slack on data engineering and search infrastructure. I used to work at Cloudera doing data science-y sorts of things, and I used to work at Google doing all sorts of things too. But what I want to talk about today is some work that I did over the course of the year with a group of folks, kind of a very diverse group of folks at the Department of Public Health in California, with a team of epidemiologists at Johns Hopkins, and a bunch of folks from AWS. During the early stages of the COVID-19 pandemic in California. So the chart I'm showing here is I grabbed this image from Gavin Newsom's Twitter account. This is a chart which sort of showed some of the early projections, or I suppose as we call them, planning scenarios around COVID-19 in California back in April that this team generated on sort of on demand, very, very quickly under very stressful circumstances back in March and April, May and June. So yeah, this is kind of like how I spent a good chunk of this year. I want to talk a little, I guess I had a few things I wanted to say before I get into the rest of the talk. The first thing is I am not an epidemiologist. And although I've been working, in the tech industry for like 20 years now, I feel like I'm just kind of maybe barely starting to be sort of okay at software engineering. So I'm not an expert in epidemiology. So anything I say that sounds like related to epidemiology, y'all should probably take with like a grain of salt or double check with like actual epidemiologists. So I have no kind of pretense to be an expert in this stuff. The second thing is, like everybody else, I have a lot of, personal feelings about like lockdown and public health responses and how the government has behaved. They're complicated, and I'm not really going to talk about them today. They're not really relevant to the kind of the stuff I want to talk about. What I do want to talk about though is my experiences and what I learned about building like very data and compute intensive workflows in the service of science under the most stressful conditions I can imagine, because I thought that work would be useful to everybody who does machine learning, who does data science, who does any of this kind of stuff. I think the experiences there, I think, will resonate with y'all when you think about your own experiences in your career and all that sort of good stuff. So that's what I want to talk about today. So the work I'm talking about here started the week of March 14th, 2020, which I think I saw a joke go by earlier that there were only really 2 days in 2020, like March 14th and November 3rd. It looks like maybe November 3rd is coming to an end, which I'm grateful for. Ideally, it will end while I'm giving this talk. But that's sort of roughly when this started. And the work I'm going to talk about ran through roughly June of 2020 now. So in early March, like everybody else, I was, panicking and kind of freaking out. And I got a call one day, it was a Saturday actually, from a guy named DJ Patil, who works at a company called Devoted Health, but he used to be the deputy CTO of the United States. He used to be the chief data scientist at LinkedIn. I think a lot of people know DJ. DJ's been around for a while. DJ had been tracking the COVID-19 pandemic in China for quite a while, and was going to Sacramento that day to start helping out with the state of California's response to the pandemic. and he excuse me, and drink some water while I do this. He called me to say that he thought he might need some software engineering help, some data engineering help, and was I available to help out? Because he knew that I wasn't really doing much of anything else other than obviously stocking up on toilet paper and pasta. And, basically I said, hell yes, like anything y'all need, let me know. So DJ gets up to Sacramento. Monday rolls around. He starts working with the folks at the Department of Public Health. And at the time, the department is working with the infectious disease dynamics group at Johns Hopkins, who are running models, what are called planning scenarios, to sort of project in California, in every county of California, how many cases of COVID-19 are we going to have, how many people are going to be in the hospital, all that sort of good stuff. Now, the epidemiologists have been working on this problem for, I think, at least about 4 weeks at this point. This is kind of like mid-March. They've been working on this for a while. And they're not really like sleeping that much because they're doing this for a whole bunch of states. And they're running all of their models on a single very large machine that they have actually at Johns Hopkins. And so what DJ and my friend Sam Shaw and I was asked to help out with was basically providing like relief pitching. Pick up some of this model runs, run them on much bigger machines in the cloud, let the epidemiologist take a nap every once in a while so that they can like focus on epidemiology. And so that was what we set out to do. That was our sort of contribution here. Like I just said, I'm not an epidemiologist. Unfortunately, I have to talk about epidemiology a little bit for this work to make sense. The model we were running is what is called an SEIR model. And it is called in epidemiology a compartmental model. The idea is that you have a population of people. Each sort of member of the population belongs to a different compartment. There's the S compartment, which is the susceptible group, people who are potentially could get the virus but haven't actually caught it yet. E is the exposed group, people who have been exposed to the virus in some way. I is the infectious group, people who are now capable of giving the virus to others. And then R is the recovered group, people who are recovered from the virus who can no longer basically infect other people. Within the infectious group, you're going to have people who get infected and need to go to the hospital, need to go to the ICU, need a ventilator, and obviously you're going to have some people who die. And the idea of these models is that there are all of these transition probabilities, parameters that describe like transition probabilities between these different compartments. And so what epidemiologists do is try to figure out, estimate from the data they have what these parameters are, and then they can run these models forward in time to get a rough idea of how many people are going to be in each of these different compartments over time. So usually you see these models as kind of like big, like exponential curves, because that's like fundamentally what the underlying dynamics are. The reason that this stuff is computationally intensive and the reason this stuff requires software engineers is because we don't really know what these parameters are. We have guesses about what they are based on the data, but the reality is that we run thousands and thousands and thousands of simulations by doing random draws from the parameter distributions in order to project things forward. So whenever you see one of these models up at like the model hubs and stuff like that, this is the one from 538 and the Johns Hopkins University model. This is the model that I worked on over here. There's always a range of possible outcomes. So it's not simply a question of like, the mean is not actually a very useful predictor here. With the median and there's actually a much better estimate of what will actually happen. But the possibility of having these kind of out of control growths of infections and all that kind of stuff because of the exponential nature of the distribution is the thing that tends to push these means up. So it's important to know that like we're always doing thousands and thousands of simulations to account for the uncertainty around the parameters in this model. The other thing that was really important about this model in particular, at least for us in California, for the government, was that it was a geospatially aware model. If you're thinking about like responding to a pandemic, it's not strictly speaking that useful to know how many people are going to get sick in the state of California as a whole. What you really want to know is like on a sort of county by county level, how many people are going to be sick, how many resources are we going to need so that you can be sure to get your ventilators or get your hospital beds or whatever it is you have to the places where people are most likely to get sick. So The compartmental models we were working with had a geospatial component to them. Each county was kind of like a little node. And then we had transition probabilities for people moving across counties based on historical commuting patterns and stuff like that from census data. So that was sort of the other very cool aspect of this model. And then the final thing that we really had to kind of like, again, the epidemiologists had to do like a lot of guesswork around is understanding the impact of non-pharmaceutical interventions. So how are people going to respond to the model is kind of, or how are people going to respond to the pandemic? The funny thing about these planning scenarios and why you can't really call them forecasts is because showing kind of the planning scenario to people will change their behavior. So like the planning scenario that shows like an exponential growth in cases is only going to be true if no one actually believes that there's going to be an exponential growth in cases, if that makes sense, right? If I show you this thing and there's going to be like this huge explosion in cases, everyone will change their behavior in a way that means there won't be an exponential growth in cases. The funny thing about these, I guess the funny thing, sad thing, or maybe a good thing, I suppose, depending on your perspective, is that we only really get like global pandemics about once a century. And so a lot of our like our training data, our labeled data around how people behave in response to pandemics is from like 1918. It's from like the great influenza pandemic. And so data we have on like how cities like Philadelphia and St. Louis and Kansas City responded to the pandemic back then are actually like very useful in informing and understanding how people will respond to things now. And the data we're generating now from the current COVID-19 pandemic will be, I can only imagine, incredibly useful in predicting the course of like the next pandemic we have over, at some point in the next century. So those are sort of all the factors to consider: these transition probabilities, the geospatial component of the spread of the virus, and the impact of these non-pharmaceutical interventions. These are like the huge kind of parameter space that we're trying to understand and sample from when we run these simulations to get an idea of like what's likely to happen where. Okay. I want to talk about joining a new project as a sort of nominally senior person. There's a great book, which I highly recommend, called The First 90 Days. And it's a book about joining a new company or a new organization as a leader and the things you need to do to be successful over the first 90 days, the things you need to do to sort of set yourself up for success. In this context, I didn't have 90 days. We didn't have 90 days. We had about 9 hours. We had basically like one day, more or less, to establish like credibility with the technical team at Johns Hopkins that we could be useful. And this is a weird thing. I think one of the virtues of being like a senior software engineer is that I have joined a life and I have had to come up to speed like a bunch of different times. And so like the skill I've gotten good at in some ways is like coming up to speed on a new project relatively quickly. And so like it's especially like kind of a weird scenario where like we were brought in, by the State Department of Public Health. This was not something that the epidemiologists at Hopkins, like they didn't like recruit us to their team or something like that. We just were sort of dropped on them to be like, here you go. These people are here to help. We promise they won't like waste all of your time. And so I very much like felt a strong sense of being clear early on about like what I actually was capable of doing, what I knew how to do, what I did not know how to do, being very clear about like what I thought was necessary to do, like that kind of stuff. And also being very clear about like the resources that I was capable of bringing to bear to help sort of solve the problem, right? You come in with a tremendous degree of humility, right? Again, not an epidemiologist, have never run this stuff before. I know a lot about running data pipelines. I know a lot about data and compute intensive like workflows. This is sort of what I know about, and I'm happy to help with this kind of stuff. That was like sort of the immediate challenge of the project. And it sort of like, I want to call out, I guess, like a bit of good news, which is the fact that like this was even possible at all for us to join this project and help out was made possible by like a common set of tools, which is that like the SEIR model was done primarily in Python using like pandas and Numba for like the very compute intensive aspects of the simulation. And the hospitalization resource analysis was done in R, like primarily using like Hadley Wickham's tidyverse for all intents and purposes. The code for doing this was all available on GitHub. It was like shared publicly. You can look it up right now. It's actually open source. You can go read everything we wrote. So it was really kind of remarkable. And I guess like I feel very grateful for having these tools as this common lingua franca for folks in government, for folks in industry, for folks in academia. Like we speak the same language, we share the same tools, and this allows us to come up to speed and kind of like align very quickly on things that otherwise would have been much more challenging. Like if we had had to negotiate a software license or something to use the tooling the epidemiologists were using, or if we had had to like have a discussion about why source control is important, like all these things would have really slowed us down and meant that we couldn't get to work nearly as quickly as we did. And so this was like very, very helpful for us. Our immediate project in the first sort of 48 hours was essentially like a lift and shift operation, meaning there was this machine at Johns Hopkins that was running all these simulations. It was a development machine. It was very big and beefy, but there was no kind of clarity around like what were the dependencies that the Python code and the R code needed in order to run. We were using lots and lots of packages, lots of R packages, lots of Python modules. None of that was documented. And so our very first job was just like figuring out, okay, what exactly do we need in order to run this code? And so that was like most of our first day. It was like figuring out the dependencies, getting everything from the machine, putting it into a Docker file, and then building like a container image that we could use repeatedly all over the place. There was no like, we didn't bother changing any of the optimization, SEIR code itself. That wasn't important. It was just a function of like, let's get a lot of clarity, very explicit around like, what are our dependencies? And let's create a mechanism for us to run this thing on any sort of machine we need. And so that was essentially like our very first effort. That was our entire focus. I got to call out a special note of thanks briefly, because the kind of two other things we were doing during this time were really bringing resources to bear on the problem. Obviously, step one in creating any new project is, creating a Slack team for it. And so we reached out to the folks at Slack to help set us up with like, basically a free professional account so that we could use shared channels with the folks at Hopkins and the folks in California, so we could all work together in one workspace. And then simultaneously, we spent a lot of time calling friends at AWS to get more resources brought to bear on the problem, to get more vCPUs, to get more machines, to get like account limits lifted. And I'm just incredibly grateful to the folks at Slack and AWS who really, really came through for us in a pinch when we were just like a couple of randos basically saying, hey, we're helping out with this and we need some help. They were there for us, and I'm incredibly grateful to them. Once the governor made the decision on March 19th to like lock down the state, things kind of got like a lot less hairy. We were to the point where we could run things in the cloud kind of consistently, reproduce the models we were running on the Hopkins machine. The epidemiologists could rest a little. They could get some rest. We could run stuff for them. This was great. Our next big challenge was really just like the nuts and bolts, boring, standard, fundamental, but also like kind of great and magical work of like profiling the code, finding the bottlenecks, fixing them, moving hard-coded parameters into configuration files, like really just like making the code much easier to run, making it much easier to be reproduced, adding tooling to support reproducibility, all that kind of good stuff. Like the really like, sort of yeoman's work of being a software engineer, more or less, was like how we spent most of April, slowly but surely chipping down the performance so that we could run models in like a matter of minutes instead of a matter of hours, all of that kind of good stuff. And what was great for me about this, if I can just say, I guess like after leaving Slack, before working on this project, I really had not like opened a computer to write code again in like 4 months. I was super burned out and tired. And I loved this experience because I got to rediscover how much I enjoy this process just for itself. Like I just like doing this stuff. I like making things go faster. I like fixing bugs. I just enjoy doing it. And apparently I would do it for free because no one was like obviously paying me to do this work. This was all volunteer stuff. So yeah, I don't know. It's hard to talk about this stuff because it's so boring and common, but it's also just like so important and fills me with so much joy to do. So anyway, one of the things we were doing, Sam and I were running a lot of models, a lot of these runs sort of basically by hand. we would spin up a whole bunch of machines, and then on each machine, we would execute a set of commands to kick off the Python code, to kick off the R code, and kind of stitch everything together. And this, I'm a zealot for reproducibility. I really feel very strongly about reproducible computation. And so I went and found a tool, which some of y'all may know, called DVC, data version control, for making for creating reproducibility and clarity around the actual commands we were running for doing like reproducible research. So we could basically show the epidemiologists, for any given run, this is the code we used, this is the data that we fed into it, this is the exact set of commands we ran, and it's all like nicely version controlled, all nicely checked into GitHub, and all easy to reproduce. And so really, really grateful to the folks at DVC for building like just such a nice tool for me to get started with to like be able to do this reproducible research, kind of spur of the moment and on short notice. That was just incredibly, incredibly helpful. While we were doing this work, we also had a team of solutions architects from AWS who were working on automating some of the kind of manual work that Sam and I have been doing by hand, like running these models on machines, to run everything on batch. And if y'all haven't used AWS Batch, really, really great tool. Highly recommend checking it out. It's just an easy way to kind of like containerize and orchestrate massively parallel jobs across lots and lots of machines. Was incredibly helpful for us. And one of the consequences of using it was that we really got the epidemiologists excited about the idea of not just running these models on like a handful of machines, but on hundreds or thousands of machines. And so when we started talking about that, the epidemiologists decided to try out a much more sophisticated model where instead of generating kind of these parameters randomly and then running them forward every time, we would do a much more computationally intensive process of generating a set of parameters, running the models forward, evaluating the quality of like the predictions of the model against actual data we had on infections and ICU patients and all that kind of good stuff. Again, bad stuff, sorry. And then updating the parameters in order to come up with a new parameter model that would do a better job of fitting the data using like essentially a variation on Metropolis Hastings, like just an MCMC process. And so to do this, we had to run like much, much, much more computation, like about 100 times as much computation as we've been doing before. In order to support this model, presumably like in a cost-effective way on AWS, we had to take advantage of spot instances and breaking up these very, very long-running compute jobs into chunks or blocks of iterations. And you can think of these essentially as like a gradient descent process for all intents and purposes, right? You have a function you're trying to optimize, you're running a set of iterations, you're trying to take positive steps forward with each step, but you're running these things on spot instances, which are like unreliable, and you can't necessarily guarantee they're going to stick around for like the hours and hours of computation you need to run. And so you break things up into little blocks and you checkpoint blocks as you go. So if you need to run like 300 iterations in order to get convergence, you'll run, 30 iterations, checkpoint things to S3, run another 30 iterations, checkpoint things to S3, so on and so forth, so that you can restart with where you left off if things get messed up.
2-minute warning, Josh.
Okay, tons of time then. Let's do it. So when we were doing this work, we had a hard time getting these models to converge at first. And it was very confusing as to why. And it ended up actually being a very bad interaction between the checkpointing code that I wrote and DVC, unfortunately. In that we would initialize DVC for a new sort of step, one of these blocks, and DVC would accidentally overwrite the data that we had checkpointed over as sort of our new starting point for things. This took a couple of days to figure out. And I just wanted to call out, this was my mistake, in that I sort of prioritized like the reproducibility of the runs over visibility into making sure that when I moved this thing from code that was running as a single node instance to like a checkpointed blocked process on hundreds of machines, I didn't actually have the logging right away to verify that like it was actually doing what I thought it should. So yet another reminder from yet another experience, visibility is more important than reproducibility. Be sure you have your visibility infrastructure in place, your monitoring, your logging in place before you start worrying about reproducibility quite as much as I did. So what did I learn from all this? First and foremost, when the call comes, answer it. I love doing this work. This was the best working experience of my life. It was an absolute honor and privilege to be able to do this. If you ever have the chance to help out in this way, please take it. It's just do it for selfish reasons. It's an amazing thing to do. It really is. Sharpen your axe. All of the tooling, all the things I learned how to do to help out with this effort was stuff I learned like doing ad optimization and analyzing marketing spend and like profiling performance on like Slack and stuff and Hadoop jobs and stuff. That was where I learned how to do this stuff. And it was an absolute amazing feeling that like the work that we do could be so helpful to so many people like in this kind of crisis. Sharpen your axe, hone your craft. And finally, for folks who are making tools for machine learning, make those axes easier to sharpen. The tools you create are incredibly useful for everyone, for scientists, for researchers, for everybody. Yeah, make them easier to sharpen. Think of me, sleep deprived, trying to get your ML monitoring tool up and running in a crisis situation, like in nothing in March, when you're thinking about the developer experience for your tooling. Make this stuff accessible, make it atomic, make it easy to use. Can't emphasize this stuff enough. It's just the best. And finally, last but not least, thank you to these people. This was the team of folks I worked with across EPFL, Hopkins, Utah, AWS, and random folks in Silicon Valley. Thank you all so much. It was an absolute privilege to work with you. And with that, if I have any time for questions, I am happy to take them. Otherwise, thank you so much. I really appreciate it.
Thank you, Josh. Thank you for this work you did. Okay, folks, we are technically on a break and have just a moment or so until the next talk, but we have time, I think, for one question from Carlos. Can you give us a general idea, the ballpark numbers, for how many different models were you running?
Yeah, it's a great question. So we were running on the order of 10,000 different simulations, using a combination of assumptions around how people would respond, like what the NPIs would be. We really didn't have a good idea of how deadly the disease was back in March. So we had to do a bunch of guesses around like how many people will get infected, will get hospitalized, all that kind of stuff. So generally speaking, it was kind of 10,000 runs, 10,000 simulations across, I think there were something on the order of like 150 counties we had to simulate, or 150 geospatial units in California. So like 150,000, am I doing my math right there? Yeah, 150,000 simulations, or 1.5 million, something like that. Something on the order of magnitude.
Okay, one of the two. Well, folks, we do have more questions for Josh regarding some modeling and some data pipeline, but we're out of time. So Josh, if you could stay online and answer via chat, or
I'd be happy to. Anyone can DM me, I'm happy to do it. My pleasure. All right.
Thanks again.
Thank you.